Yeah, it's been like, yeah. This is coming in. I think it's just because there's a lot of not even parts to get the feedback. Yeah, like, you know what I mean?
Does anybody else have a presentation they want to put on to the desktop that's ready to go? Do you have one you want to put on here? You're not Malaria Highlands, are you? You're not part of the group that sent you something, no? I think if you stick it in there, actually, is the way it's set up at the moment. It's easier. Yeah.
Which one did you choose? It's interesting. I probably should have gone for like soils and sometimes it's nice to do something like that off the top right.
I think it's not going to just be 5 of us.
Yeah. I wasn't expecting it to be like this.
If it is just us, I think I probably won't share the rest of the slides with everybody else. I'll just make it a closed group. I'm sure there'll be more.
Yeah. There's a shower actually. I mean, there's a good percentage of the world went to fire. Yeah, no. Sorry. Who else is producing this with that?
So, what's your presentation on? What topic did you go with?
That makes sense. Well, one of them was in Greece, and then oh my god, in China.
It's okay, we'll see in a minute. I'm just wondering if we're going to have a mix, well, assuming more people turn up, I'm just wondering if we're going to have a mixture of topics, which is what I'm hoping for. We'll see. So, have any of you guys got a presentation or a paper?
Yeah.
What's your paper?
Vector-borne diseases, ERDs.
Okay. Right. So, are you together or you guys were separate? Is that right? We're going to do something potentially?
Yeah, I didn't. You were in your room.
Yeah, I was not on my own.
Oh, okay. Right. Are you able to go and put it on the computer?
Yeah,
Is that
of course.
okay?
It's fine.
It's not as nerve-wracking.
There's 6 people. I could probably get a paper out. Just skim it.
It's not coming up.
But look, sometimes it just takes a long time to think. Let's have a look. If you stick it in here, actually, it works. I think it's set up to detect it from there at the moment. Yeah.
Yeah, bro.
Okay.
Okay, I'll just grab my notes.
Yes. There's no rush to do anything.
Oh, okay, that's fine.
I just thought we'd get them on the desktop.
Oh,
That was
okay.
all. So if you want to copy
Alright,
it
yeah,
onto
I'll
the
just get it
desktop,
up now then.
and then you can take your USB stick with before we need it. Hi there.
Where would you like it? Sorry.
Just pop it on the desktop, I think, anywhere, and then
One
we'll.
of your 2 of the lecturers
Sorry, I'm not.
It's okay. We always talk to them, they always just complain about like having to, is it right? Yeah, and then you just struggle. Oh yeah, I did like that. He was like really tough on the exam as well. He just, I didn't answer any of his questions because he was like, you need to get everything like.
So as a matter of interest, are you guys environmental sciences?
Scorer.
Okay.
Biology.
You're biology. Are you biology or?
Yeah.
I think we should start. I think, what do you think about moving forward a little bit so that I'm not screaming at the back of the room? That would be so, what I was planning to do was that we would have quite a big session on going through lots of different presentations, but we actually have quite a small number. So, we might have to rethink it very slightly, well, unless there are more people to turn up all of a sudden. Have you got a presentation? Okay, in that case, I think we'll do a combination. We'll do the presentations that you guys have brought. I've brought some extra papers. Maybe you can work in groups on those as well, and so you'll have to double up on the presentations. I'm basically going to do a presentation too, which is kind of a case study on malaria in Southeast Asia, which is something that I work on, so I'll go into a bit more detail obviously. And then the idea was to have a bit of a question session and debate at the end. So were you able to read the papers that I asked you to read? Yeah, the writer paper and the Ogden paper. So I just wanted to talk about those briefly, and then I think we'll go into your presentations. Then we'll have a bit of a group breakout, and then I will do my case study, and then we'll do all the rest of the questions. This is my one. So just before we go into your group presentations, so I just wanted to sort of talk about those papers briefly, especially the writer one. So just really a reminder, I showed you this figure here in the last lecture, and it comes from that Ogden paper. And this basically tries to capture all the sort of biological mechanisms that might underlie why vector-borne diseases respond to climate change. So for the parasite in particular, it's really based on this extrinsic incubation period. How long does it take for the parasite to develop? And it develops more quickly at higher temperatures, and it stops below a certain temperature. So obviously that's going to a large extent determine the distribution of disease. And then for the mosquito and the mosquito's interactions with hosts, there's a whole range of different things that could happen. You could have increased population sizes, increased lifespans, wider geographical distributions, things like increased activity that could result in increased feeding on humans. Feeding may go on for longer. There will be potentially increased breeding sites as a consequence of increased rainfall, increased inoculation rates if they're more effective and feeding for longer, and potentially it can enhance breeding activity as well. So generally speaking, the idea is that increased temperatures are going to be beneficial for most mosquitoes most of the time. So given that, and looking at that, the writer paper, which was talking about I can't remember quite the phrase that he used, putting the horse before the cart or something. Why do you think that we don't have malaria in the UK, Western Europe, or the States? So you always see these distributions, don't you, of vector-borne disease, especially malaria, and it's all in the tropics and subtropics. So why is that the case? So did you read his think you must have read this paper. Yeah, the write-up paper. So this is a character who is, I think he's probably a reasonably old gentleman now, who's been working on mosquito vector-borne disease for a long period of time. And I think you could see that, well, I thought he was quite opinionated, and you know, he's coming at this issue from a very particular point of view, isn't he? He's, I don't know, what did you think? What did you think of this paper?
It was interesting, like the bit about I didn't know that they were travelled on, you know, like the container boxes.
Oh right, that was the Aedes aegypti, is that right? Yeah, yeah. So, so that was new to you, was it?
Yeah.
I might have mentioned it briefly in the last lecture, but perhaps I should have gone into a bit more detail. So that's about Aedes aegypti originating from Africa. Is that right? Or was it Aedes albopictus?
I'm not sure, I think.
Or was it another one?
I can't remember, the tyres one from Japan.
So again?
Tyres.
The tyres,
Yeah.
okay, so that's Aedes albopictus that we very briefly mentioned in the first lecture. So that's a mosquito from Southeast Asia that's travelled around the world in the tyres, yes. So that's a change in distribution, basically down to globalisation and trade. So I think it's also been spread, that's probably the main way it's spread. It's also been spread in, I can't really call it, you know those little like living bamboo pot things that you can buy? Have you ever seen them where you get like a few sticks of bamboo as like a decoration? So those have been imported. And then sometimes those have been found to have mosquito eggs, and then they start to proliferate. So that's the reason that things like that abound in places like Australia, but it is mainly the tyres. Well, if you haven't read this paper in depth, it's really worth reading, because this is somebody who has worked on mosquito-borne disease for a long period of time and really deeply understands it. And one of the things that he goes into, and he seems to have a bit of a feeling despondent about, is the distribution of disease and malaria, and the fact that it's not inevitable that it's only found in tropical regions. So did you know, for example, that we used to have malaria in the UK until fairly recently? Yeah, so it was here right up until I think about the 1920s when local transmission essentially stopped, and it was in the marshy areas, so in Kent and Essex and the fen areas where there's lots of marshland, you get a particular species of Anopheles breeding that's called Anopheles atroparvus. It's actually found throughout it, and some other species are found throughout much of Europe. So it's not the case that you only get Anopheles species in tropical regions, okay? And these are perfectly good vectors for malaria. There are enough people to feed on, and that provided the mosquitoes choose to feed on people, and providing they're able to transmit the parasite, there's no reason why you can't have malaria in northern regions. So if you think about that R0 equation that we were looking at the other day, and all the parameters in there, so as long as those conditions are met, then you are going to get malaria transmission, and you're going to be able to keep R0 greater than 1. So in the UK we have the vectors. They go actually even fairly far north, through Yorkshire, and I think there's been cases of malaria transmission historically as far north as Scotland. So latitude is not a barrier to malaria transmission. So it's thought that Oliver Cromwell, for example, actually died in part of malaria. And it used to be the case that that in those areas, people who moved into the area would frequently die. So there was actually a huge mortality rate. So husbands looking for wives would bring in wives from a different area, and actually they would end up going through huge numbers of wives, because essentially their wives died one after the other because they just succumbed to the local malaria, whereas if you were from that region, you had built up some immunity to malaria. So it used to be a really serious problem, and it was, so when you hear about the ague, which you've probably heard of from history books, we think the ague was malaria. And then there's also something called quartan fever, which is where With malaria, you get these periodic fevers that are caused, and with quartan fever, I think it's a longer time between the fever, so 3 days instead of 2 days, and that probably indicates that we had both Plasmodium malariae, and actually I realised that that's a mistake. It shouldn't be Plasmodium falciparum. I'll change that before I make the slides available to you. It's actually Plasmodium vivax that we would have had throughout much of Europe. Okay, so there's two main forms of malaria, falciparum and vivax, and so it would be mostly Plasmodium vivax that we had, but we probably also had Plasmodium malariae because it has the greater intervals between the fevers, and that's where and we think that that's the case because of this quartan fever. And in Italy, it was actually there until well after the Second World War because there's lots of marshy areas around Rome, and it was a really problem area in Rome, and there was lots and lots of malaria. There's still malaria in Eastern Europe. There's been huge malaria epidemics in parts of Russia, actually even fairly recently. So there's no real reason why we can't get malaria in these regions, yeah?
You know, because there's so many mosquitoes in Rome anyway, could the vector easily be like brought in like soon?
The vector or the parasite?
Both.
I mean, I think so. What's happened in Rome is that essentially the marshes were drained to make way for expansion of the city and just general land use change. So that got rid of most of the vectors. So the local vectors have gone down, and that's essentially what mostly got rid of malaria, that and some DDT spraying. But there probably still are some, so there is the potential that you can get local transmission, and there's been 1 or 2 incidents of that in the UK, where somebody in Essex has got malaria even though they've never left the country. And that's because the traveller has come in with malaria, transmitted the malaria to the local mosquitoes, then those mosquitoes have bitten someone who's never been out of the country. But essentially, because our health service is pretty good, mostly, that transmission gets stopped very quickly. So in the Italian or Rome situation, you could get exactly the same thing if there was still vectors there, the parasite coming in from travellers. But you could also potentially get different vectors setting up as well, that's true. It doesn't seem, I'm not quite sure how easy that would be to happen. So with the Aedes mosquitoes, so these are the ones that, like the Aedes albopictus that's been transmitted in the tyres from Southeast Asia to the rest of the world. And then the other Aedes mosquitoes are the Aedes aegypti that have been travelled through the rest of the world, probably just breeding in small containers of water on ships. Their biology is particularly conducive to globalization. You know, so the fact that their eggs can dry out and survive, or the fact that they breed in these small pockets of water, means that they've been able to spread around the world. I think for most anopheles that would be much more difficult to happen.
What's the difference between Aedes and anopheles? They just
they're completely different groups of mosquitoes, so different genera of mosquitoes. So the 3 main groups, which was something I mentioned in the first lecture, are Culex, Aedes and anopheles. So it's only the anopheles that transmit malaria, but only some of those. There's loads and loads of species of Aedes mosquito. Many especially are found in African forests and are involved in zoonotic disease transmission there. That's where Zika originated from, and chikungunya. And as I said in the last lecture, they've essentially adapted to humans, and they have become able to breed in human habitats. And we think that they spread around the world by going into containers on slave ships. So they would have obviously been storing water, fresh water for drinking. The mosquitoes would have bred in there. They would have been feeding on the people on the ships. And so essentially, by slave trading, we exported the mosquitoes and the diseases that they carry. So yellow fever went from Africa to Latin America, and Zika and chikungunya have now spread around the world. Okay, so globalization has been a human movement has been a pretty major factor in spreading some of these diseases. And it, obviously we're still moving around the world massively, so that's still going to be an issue, yeah.
So you know the chicken, I think it was the first page, mentioned the chikungunya was in Italy.
Yes.
Was that like during the slave trade, or was it kind of after?
That was just really recently, actually. That was just a few years ago that chikungunya was in Italy. So there was a really recent outbreak that went from the east coast of Africa, and it travelled to, I think, to Southeast Asia, to the Indian Ocean. It went to India, and some travellers went to Italy. And because that, in this case, it wasn't transmitted by Aedes aegypti, it was transmitted by Aedes albopictus, which is the species that's moved from Southeast Asia to Southern Europe in the tyres. Okay, so I'm sorry if it's a bit confusing, because I think I introduced some of these things in the first lecture, but I know there's lots of different names, but actually in this paper I think he does a pretty good job of explaining the background of all these diseases. But yeah, so that transmission in Italy is really recent, and obviously then the transmission in Latin America was, I think you've all heard about that, it was very much in the news. Before Zika was in the news, it was chikungunya. Do you remember the reports? Maybe you're too young. So it was just a few years ago. So in Europe, it's been transmitted by Aedes albopictus, the chikungunya virus. In Latin America, it's transmitted by Aedes aegypti. So Aedes aegypti is a much more tropical species because it originates from the forests of Africa. Aedes albopictus is from Southeast Asia, but from fairly broadly in Southeast Asia and quite far north up into to China and Japan. So it's much more tolerant of colder winter conditions, and that's why it's been able to spread into southern Europe. Okay, so that's a mosquito that could really potentially spread much further north in Europe, especially if it's able to adapt to changing conditions. So I guess what I wanted to do is just to dispel the possible myth that you may have succumbed to, but perhaps not, that vector-borne disease, things like malaria, is only a disease of the tropics. It isn't. And so then the question is, well, how come we still have malaria in the tropics, but we don't have malaria here? And I think he talks about that quite a bit in here. So in the UK, it was essentially land use change. We drained the marshes. We actually drained the marshes pretty much before we even knew they were involved in malaria transmission. That was sort of incidental. In the southern US, they had a lot of malaria actually until the 1930s. So it was, if you can imagine the southern states, it's very warm, humid, actually amazingly good mosquito breeding grounds. If you think of those kind of like Louisiana swamps and places like that, fantastic grounds for mosquitoes that can transmit malaria. So again, with the slave trade, people took, especially slaves from West Africa, to the Americas, who brought with them the malaria. There was already a local Anopheles vector, so there was no transfer of vector in that case, just the transfer of the parasite. So that was a big problem in the States for a long time. And essentially, what changed that was agricultural change, because the consequences of the agricultural policy that were put into place meant that there was a massive depopulation of rural areas. And again, if you think back to that Arnold equation, everything kind of always comes back to that. One of the things that you need in there is the human population. So numbers of humans are going to affect disease transmission, because you can increase the absolute number of infected bites. So when you have more humans, you can also get more malaria transmission. So by reducing the human population and taking them away from the vectors have to feed on something else, and that stops malaria transmission. And of course, fancy houses. If any of you've been to the southern states, they have these screen porches around their houses to stop mosquito biting. And there's plenty of Aedes aegypti that have gone in, and Aedes albopictus that have moved into the southern United States. So that but we don't see reports of Zika or chikungunya there, do we? So, you know, so there's a big question then as to what's different in Europe and America compared to the tropics and why they have disease and we don't. And I would have thought the obvious, I mean, what do you think are the obvious differences? Sorry?
The economy.
Economy, yeah. So basically, amount of money.
Yeah.
how many dollars there are per person to look after, you know, the public health services, infrastructure. Education is a big issue as well. So, you know, I think I showed you those brick pits in Africa where people were, you know, going about their normal business, making bricks as one would, but actually giving everybody in the village malaria. And that's an education issue in large parts. People just didn't really know that that's what was happening, that the mosquito larvae were breeding in those pits. And actually, I don't know, I guess all of you in this room have probably known for ages that mosquitoes transmit malaria, but it took ages before people knew that. So in Europe it was called malaria because it was thought it was related to the bad smell coming from marshy land, so it was called bad air or malaria, and that's where the name comes from. And we actually only realised about 120 years ago, it was a captain in the Indian Army, Ronald Ross, who worked out that it's mosquitoes that transmit malaria. And to you, I'm sure it's just so obvious that they do, because you've been taught that for a long period of time, but it was really hard to demonstrate it, and it was hard for people to really recognise that it was the mosquito bites that were giving them the disease. And so to educate people, if you go out to rural areas in Africa, for example, it can take time to convince people that it really is the bites of mosquito that are giving them these diseases, because they'll say things like, but so-and-so over there gets lots more mosquito bites and they never get malaria. But that's because it's a different environment, different species, and it doesn't transmit. So education is also a massive part of it, and having access to, obviously, to healthcare. So it's very much a disease of poverty, really, in its current distribution. So what would be great, I think, is if you guys could give your presentations. We can then, let's see how we feel at that point. Either I can go through my kind of longer presentation of a case study of malaria in Southeast Asia, or if you want, we can look at a few more papers as well that I've brought along. And then at the end, I just wanted us to have just a general discussion about some of the issues surrounding mosquito-borne disease transmission and how useful climate models are in helping us understand what might happen in the future. Does that sound okay? Who wants to go first? I'm actually really interested to see what examples you've got. So I will come back to this later. Which one was yours? I think we can ask a few questions at the end maybe as well, if that's okay, but nothing horrendous.
Okay. So my article talks about the effect of climate and climate change on vectors and vector-borne diseases. So it reviews important differences in the biology of two important groups of vector, the hard body ticks and the diphtherians.
Which just means flies.
Yeah. And their life cycle, their life history and their behavior are very different, so maybe they can respond differently to change in weather. So if we look at their life cycle, the ticks have 4 stages and live a very long life, and they have high dependence on reproduction on host and low dependence of reproduction on habitat. And for flies, it's the contrary, so they live more than 4 stages, but they live shorter. if we talk about their behavior, the ticks and the insects, both can be domesticated or wild animals, but accidentally humans too. And the ticks spend days feeding on hosts, right? And septarian spend
Flies, you can just say
flies. Okay.
Yeah.
Flies only spend few seconds on the host, so it's quite different. Now the temperature increase or the humidity decrease affect less ticks than flies. But for both of them, because they spend energy on changing of habitats because of the temperature changes, they have less energy and less time to feed on the host. And
So can you explain, sorry, why are the ticks less affected by
I
temperature?
talk about that just after.
Okay, sorry.
And for rainfall increase, ticks are less active and the flies reproduce more and the density of the population is bigger. So in general, ticks are less affected by the increase of temperature because they have long life cycles, so they have time to adapt and find solutions or move from one area to another during their life. And rainfalls aren't a good point for them because they don't use water in their life cycle, so it doesn't really affect them much. And for flies, they are very affected by temperature changes because of their short life cycle, so it's the contrary, they don't have time to adapt and find solutions. But rainfalls are good for them because they have an aquatic part. They live in the water during one stages, I think, of their life cycle. And as we say, they have short life cycles, so they respond rapidly, in general badly, or they can die, or they can maybe find solutions, but they respond very rapidly in general to changes. Yeah, that's it.
Okay, thank you. So, questions from you guys?
What sort of diseases do each of them?
The
like, big
ticks
ones?
more transmits Lyme
Lyme disease.
and
yeah.
flies, I think it's pest.
Oh, okay. Thank you.
So if I get you right, then what you're saying is that that the ticks are kind of almost like more generalist, if you like, that they're able to be. So you use the word adapt, that they can adapt to changes in the environment. So people use the word adapt in different ways.
Yeah, it's during their life, not in general.
Not an evolutionary response.
Yeah,
So they have this kind of what I would call a plastic response, where they can modify how they use the environment to cope with those conditions. So I imagine as well, if they're on the host, that it's kind of like a microclimate almost, isn't it? Because they spend a lot of time, I guess they spend a lot of time on the host, and then they spend a lot of time in the grass or something like that as well? Or do they crawl off and find little places?
I don't really know.
Okay.
Sorry.
I'm less familiar with ticks than with the flies, but yeah. So, and one of the things that actually was brought up in the writer paper is that, so you're right that generally speaking that with the flies they tend to have a very quick reproductive cycle, and it's sort of burst or boom, and the population sizes very much depend on the environmental conditions. But one of the things that we really don't understand about them, and potentially has a massive impact on vector-borne disease, is what happens in either the cold season or the dry season. So in Europe, obviously the mosquitoes that we have, and they go, they cover right the way across Europe and North America, they clearly are adapted to surviving cold winters. But we don't really know exactly how they do that. Probably they go and hide in little nooks and crannies, and maybe kind of Easter bait or something like that, kind of go into some sort of torpor, or they might lay eggs that then can survive the cold and then hatch. So you get some mosquitoes that leave their eggs in these kind of frozen little pools, and then they hatch out. And then in the tropics it's a similar problem, but it's the dry season that's the issue. How do they survive through the dry season? And again, we actually don't know what happens during the dry season. We think that they probably go and hide in little nooks and crannies here and there. And it would be a really, and it's possible that the parasites, the malaria parasites, can actually survive all of that time in the mosquitoes. So as well as being in the host, the disease might actually also potentially survive in these very long-lived mosquitoes as well. Yeah, it's really hard to study, because how do you find a little mosquito that's in a nook and a cranny? So we kind of know almost nothing about it, even though it could be a really a good point to control them, because there is such a small population size at that point.
Because bumblebees bury themselves, don't they?
Oh, I don't know. Do they?
I think bumblebees, the queens, bury themselves in soil, like under the ground, to keep themselves at a certain temperature and like stay at stasis. And then when it heats up, they'll then be one of the first to emerge and set the nest.
Yes, I mean basically any insect that's from the northern climate, or from an area of the world that has periodic wet and cold, wet and dry periods, is going to be adapted to it, isn't it? So this idea that you have to have heat to have mosquitoes that can transmit malaria and to have malaria transmission isn't completely accurate.
Yeah, because that's what you hear on the news all the time, isn't it? When we heat up, we'll get malaria.
Yes, and it will help that extrinsic incubation period shorten, and there might be a longer period when the parasite can survive. So it might be the case, but probably a much bigger determinant is how many vectors are there, and so yeah, can be very misleading. Thank you very much. Who else wants to go? Don't have any more presentations. Did you guys bring a presentation? You always said no, didn't you? Is there another one? Great. I think it should be on the desktop.
Yeah. So I looked at Jones et al. 2008. So basically they were looking at whether climate change was going to affect disease transmission. So at the bottom you can see with these white sections, so in this first one on the top left, that shows the white section as viruses, and then in the second one along on the top, that shows the white section as zoonotic related. So it was seen that zoonotic diseases were related to 52% of the emerging infectious diseases in the most recent decade, and that vector-borne diseases were with 22.8% of the emerging infectious diseases. In the last decade, it was seen that 28.8% corresponded with the climatic anomalies of the 1990s. So it was seen that vector-borne diseases were seen to increase because of the climatic anomalies. It was also seen that latitudinal spatial gradients with the human pathogen species increased towards the equator because of the environmental parameters seem to promote pathogen transmission in the lower latitudes. Also, the wildlife host species richness increased the emergence of the zoonotic emergent infectious diseases. So whether the temperature is going to impact where the animals are, it could possibly impact where the vectors are because of them feeding on the animals. And then this shows like the percentage where it's expected to increase. So we've got vector-borne pathogens in the bottom right-hand corner. So you can see in China, especially like near the Himalayas in India, and then kind of along the equatorial band, there is a massive increase. and with the top left one with zoonotic, it's kind of the same kind of pattern. So because they're heavily linked anyway, there's, I can't remember what paper it was, I think it was the Rita.
Yeah.
It said that one of the diseases with people farming pigs, the vectors were surviving by feeding on the pigs.
Japanese encephalitis.
Yeah, I think so. So if a lot of the vector-borne diseases are linked with the zoonotic wildlife diseases, you can see that these areas are possibly emerging disease hotspots. It was also seen that areas where the issues had already happened, people were putting the funding in, whereas they should be focusing on like the areas that are going to be predicted. But the issue is a lot of the areas where there was the zoonotic and vector-borne diseases, there was a lot of the reporting effort was low, because in like the richer countries, if someone gets malaria, they just go to the NHS and tell someone, whereas a lot of the cases weren't reported. It was seen that this is going to greatly impact the global health and economy, and then the paper kind of concluded that the resources are poorly allocated and that they basically need to change where the funding is going to for climate change, because it's going to increase it. That's it.
Oh, go back.
Sorry.
So what information were they putting into their models? So it's not just climatic data, is that right?
No, they looked at 335 like basically like outbreaks of infectious diseases between 1940 and 2004. So they saw in the 1980s there was a peak because of HIV, but I just kind of looked at the zoonoses and the viral, or I'm not sure what prion means. Prion. But they linked them in together.
Okay.
But either way, it was seen that in the last decade it wasn't increased with climatic anomalies of 1990s.
Okay, yeah. So I mean, I don't know if you got that from, thanks, that's great. I don't know if you got that from reading, I think it might be the Writer paper or the Ogden paper, even both of them, that, you know, up to date, it's very, because there hasn't been crazy amounts of climate change yet, it's extremely difficult to link any change in vector-borne disease to climate change, especially if you consider all the other things that are going on, all the other factors that are altering vector-borne disease, like introduction of bed nets and all the rest of these things. So actually, getting evidence to show that it's happened already is really, really difficult. There's extremely good evidence that climate is related to vector-borne disease, and we use that in the modelling. So in the last lecture I talked about the ENSO effect, and so that's a big part of a prediction of vector-borne disease based on climate. So I don't mean long-term global climate change, but a relatively short-term on a kind of a few years variation. Yeah, so there's a huge effort there in trying to be able to detect when that's going to happen, so that you can potentially go in and input resources where they're needed. So the case that we looked at, I think I showed you Rift Valley fever, didn't I, in Africa? So because there was the flooding that flushed out the eggs from the Aedes mosquitoes, and so actually, potentially you could predict that, because you see the change in the vegetation that starts from the increased rainfall a few months before you actually get the massive disease outbreak. And it's the same is true with malaria as well. So with malaria, the mosquito numbers tend to build up with the rain season. And again, I showed you that short-term seasonal effect. So as the rains increase, you usually get an increase in mosquito numbers, and typically malaria peaks just at the end of the rainy season. So that means if you have a longer than usual rainy season or more rain, you can see changes in the vegetation that you can detect with satellites. And so from remotely sensed images, you can potentially predict in advance when there's going to be malaria outbreaks. So that's a really big thing. But that's just that's a short-term thing. That's not talking about these long-term global climate change predictions. It's hard to, I think, go from that kind of prediction to longer-term prediction. Does anybody else? Yeah, go on.
So is it possible that climate changing patterns in rainfall is going to be a bigger impact than the actual temperature change?
It might be. I mean, again, I think it's going to depend on how much temperature, how much rainfall, which species, which disease, because everything is, and that's one of the things, again, I was trying to highlight in the last lecture, is that there's a huge number of vectors and huge number of vector-borne diseases, and they're all very different in how they're going to respond. So it's hard to say, I think, and I suspect it will be very difficult. I think there are no more presentations from you guys, are there? I think I should go through my presentation now, and then we can either decide at the end of it whether we're going to look at some other papers that I brought with me, or if we just want to talk about the questions for quite a long time. I'll ask you at the end of this what you want to do, I think. So I decided to be indulgent and to talk about kind of an area that I've worked on for a long period of time, which is malaria in Southeast Asia. Is it this one? Yeah. It's much less studied, I would say, on the whole than malaria in Africa. Let me get that. Okay. And it's a very, very different disease. Obviously a completely different set of vectors. So the vectors in Africa are mainly Anopheles gambiae. I don't know if you've heard of these species before. Yes, no? Yeah? So Anopheles gambiae and then Anopheles fenestus are the main species in Africa. And I think I showed you an image last time of kind of like open sunlit pools, which is where they tend to breed. In Southeast Asia, it's a very different picture. The environment's very different. It's much more forested, or historically, it was much more forested before humans kind of cut down all the forests. So as a consequence, a lot of the mosquitoes in Southeast Asia are more adapted to much moister environments, and a lot of them are adapted to forests. So this species is Anopheles dirus or Anopheles bimite, goes by both names. And then there's another species as well, Anopheles minimus, which is a major vector in the forests in Southeast Asia. So for the last several decades, as malaria has been studied there, it's always been considered a disease of forests and the forest fringe. So people who live in villages at the forest fringe in Southeast Asia are the ones that are at risk primarily at getting malaria. And so this paper, which was published in 2016, was looking at predicting the changes in malaria risk as a consequence of climatic change. So they built their model using climatic data, which was based on Anopheles species and the climatic variables that are conducive to their growth. They did that in a very general way. So there are about 32 species of Anopheles in this region that can potentially transmit malaria. Not all of them are major vectors, but certainly 5 or 6 or 8 of them at least are major vectors. But they've just considered Anopheles in general, just as a group of mosquito species. So I think that's potentially one issue with the modelling. Nevertheless, doing that, they were able to, they tested their model. So this is the distribution that they got for the distribution of malaria. And actually they found a pretty good match with the actual distribution. So this is about a 90% match to the actual distribution of malaria. So they had a reasonable model in terms of Anopheles abundance and the climatical variables that would give rise to sufficient vectors to transmit malaria. And so they used that as their basis and then looked at the effects of climate change to see where you would expect an increase or a decrease in malaria transmission. And essentially what they found from the model was that there was I think these are different time periods. This is 2050 and that's 2100. Essentially what they found is that there should be a decrease in malaria suitability especially in parts of India, the north and the east of India in particular, and a decrease in some of these southern regions in malaria as well, but that there would be an increase in malaria as you go kind of northwards up into China. So essentially a kind of a northern shift in the distribution to a large extent. And essentially that came from the model because of changes in heat stress. So, so the predicted decreases in malaria essentially were due to heat stress. So they were saying that in these locations, as climate warms, it's frequently going to be above 40 degrees Celsius, and that's not conducive to mosquitoes. So a big question would, of course, be whether or not, what's the potential for the mosquitoes to respond behaviourally? And that's again in the Writer paper. He talks about the fact that, you know, mosquitoes are not just objects that can't react to the environment. They obviously have some biological limitations, but they can do things like seek shade. They often seek shelter in houses which might have increased humidity compared to the outside, or decreased temperatures. So this is very much a climatically driven model. It's not, we don't know really how the mosquitoes would actually respond behaviourally. And then this is just the opposite side of the coin, the changes in cold stress. So essentially they're predicting kind of a northward distribution. So this is the actual distribution of malaria at the moment in Southeast Asia. So interestingly, some of these areas are kind of conflict areas. This is the Thai-Myanmar border. It might be part of the reason that this is a high area. And I'll show you some other data later which might also indicate a reason that this is such a high transmission area. We have these areas, so this is Myanmar here. This is actually Rakhine region. So I don't know if this malaria here is related to political disturbances, low socioeconomic status. Also there's a lot of forest left in this region, so that means that the forest vectors of malaria can survive very well. Over here in mainland India, it's a completely different set of vectors that are transmitting. So here, traditionally the vectors were thought to be these forest species, Anopheles bimai, or Anopheles dirus, goes by two names, and Anopheles minimus. Over here, the vectors are thought to be mainly Anopheles culicifaces and Anopheles fluviatibus. And what I wanted to point out was this spatial heterogeneity in malaria transmission that could be due to many different things. And what I was going to talk about was a study that we're doing at the moment on malaria. And it's actually between, it's kind of a strange region, geographical region, between mainland India and Southeast Asia. So it's actually a part of India, so this is northeast India, but it's in a really strange location. So this is Bangladesh here, and Bhutan to the north. And there's actually a really kind of like narrow little corridor of India that goes through and connects it to the rest of northeast India. So this is Myanmar and going into, further across into Thailand, etc. So it's kind of at a geographical junction, if you like, between the Southeast Asian region to the east and then this Indian region to the west. And most of the species here and the whole biogeography of this area is essentially Southeast Asian. So the forests are very wet and moist, there's a huge amount of rainfall, and the species that you find here, the birds, the butterflies, everything is pretty much Southeast Asian rather than Indian. So we expected the vectors here to be Southeast Asian species, and we expect to see forest malaria that's driven by Anopheles bimai mosquitoes and Anopheles minimus mosquitoes. So we chose, well not me, but the other people in this project that I'm working with chose to work in Meghalaya, which is this state of northeast India here. It's just above Bangladesh. It's a really underdeveloped area. It still has quite a lot of forest cover. And the institute that we're working with is in Shillong, and the malaria study sites that were chosen because they have quite high malaria over here in it's called the West Khasi Hills, and then also in the Jaintia Hills as well. And the people in this area are actually not ethnically Indian either, they're Southeast Asian hill tribes. So they look very, very different. They're not ethnically or culturally Indian at all. Right, they're classified as, I think, vulnerable groups by the Indian government. So, and what I wanted to point out again is that, again, you see this spatial heterogeneity in malaria transmission. So this is, in the Garo Hills, we have huge amounts of malaria, less so over here, and then again, quite high amounts in the Jaintia Hills. And you see this almost at any spatial scale that you go to with malaria, that there's always this heterogeneity in transmission. And this can even go down to transmission within a village. So if you go to a village and you survey people for malaria, it's not uncommon to find that it's people just on one side of the village that are getting malaria, or people on a particular side of the village repeatedly getting episodes, and it's less common on the other side. And that's essentially due to proximity to larval habitats, because mosquitoes won't fly any further than they need to get a blood meal. So they'll tend to come in, if there's a suitable habitat on one side, for example a forest, they'll come into the village and they will bite the first people they come to. So it's not really surprising that you see that. And you can imagine that that's quite a difficult thing. Those sorts of local variations are quite difficult to take into account perhaps with the climatic modelling. But that's the reality of malaria transmission, that it's the more refined the spatial scale you go to, you always see heterogeneity in transmission. And we see this when we go to the PHCs, which are the public health centres, and look at their malaria data. These are different villages in this area. We see quite a lot of variation. Some villages have a lot of malaria and other villages have less. I have to say this isn't completely controlled for population size, but it's definitely the case that some villages have much more malaria than other villages. And this is not work that's been done by me, but by other people in the group. So there's an epidemiology team that are surveying for malaria, and they are using RDTs, which is rapid diagnostic tests. So these are now widely used in most places. So this just gives a really quick result. That's just like a dipstick that you can do on some blood. Or sometimes we have to use PCR-based methods, which are much more sensitive as well. So those are really important when you have asymptomatic people. So they're screening people who may not even know that they have malaria to see whether or not they do. And the reason for that is that because this was such a highly malaria-prone area in the past, people build up a lot of immunity, and so they end up as being these reservoirs of malaria where they're transmitting to everybody else, but they themselves are not particularly sick, or they certainly don't recognise themselves as being sick. And the level of parasitemia might be quite low, so they might still be infectious, but it can be hard to detect by RDT, so sometimes have to use things like PCR. And I mean, this project is fairly recent, but you can see just from the limited data we've got so far that actually 5 of the cases that we've detected are from the same village, and from essentially 2 or 3 houses that are really close together. I'm working with American people, so I just realised it says feet rather than metres, which looks really strange, so 277 feet apart. So again, extremely spatially clustered. And So I'm working on the vector side in this project, and we want to, one of the questions we've got is, well, what are the vectors in this area? And the choice is large. So there could be as many as 32 vector species, and it depends what you mean by a vector. So we often have what are called primary vectors. So these are species that have been consistently incriminated, and whenever you go out and you collect lots of mosquitoes and you test them for the presence of malaria sporozoites, so that's the infective stage that you would find in the salivary glands. So if they're consistently coming out at a high percentage positive, you would consider them to be the primary vectors. So if you remember, I said these were the two species that we expect to be transmitting in these forest areas. And then these are the species actually in mainland India, Culis facies fluviatilis, and then there's a whole load of other different species as well that are present and could be involved in malaria transmission. So, so one of the questions that we've got is what's happening here in terms of the changes in malaria transmission. So this just looks at forest cover in northeast India. So this is Meghalaya just here, this region. This is the Brahmaputra River, so this is a big flat valley which is in the state of Assam. And you can see over time, as it goes by, that the forest is becoming, there's less cover, and it's also becoming more open forest and less dense forest. So what you actually see is kind of a mosaic of fragments of forest and a more agricultural landscape, which in this area is typically rice paddies. So the environment is changing enormously. So what we're really interested in is not how is climate change affecting malaria transmission, but how is land use change affecting malaria transmission. So I've given you this long list here, and one of the things that we're really interested in is, well, we're interested in all of these and their role, but we're interested in Culis facies. So this is the vector in mainland India, but it's now being detected in Meghalaya, and it seems, there have been several reports now that it seems to be acting as a vector there. So with all of these vectors, as you start looking at them, you find more and more species. So Culis facies is at least 2 species, so in different groups, A and D versus B, C, E. These are different chromosomal forms. And we know that AD, which I'm just going to call A, is a major vector of malaria in mainland India. B isn't, it doesn't seem to like to feed on humans. And there have been lots of reports now of Culis facies coming up in these surveys as being infected with malaria. And actually in Meghalaya there was one study that showed that 61 out of the 63 infected mosquitoes were actually Culis facies, whereas it's supposed to be Dirus, Primide, and Minimus that are the main vectors. So the big question that we have is this as a consequence of land use change in Meghalaya, that we're moving from essentially forest cover to lots more intensive rice growing. And we are studying it in this specific region, but this is something that's really happening throughout Southeast Asia, that there's massive changes in rice production. So if you think about population growth and the effect that that has, and the need for food security, there's a huge amount of money, especially development money, being put into rice growing and improving rice growing. So increasing the amount of rice that's produced, increasing irrigation for rice. And many of those species that I showed you, especially Culis facies, but also annularis, Lusnavipes, philippinensis, annularis, cantaniatus, all of these breed in rice fields. Okay? So it wouldn't be that surprising then if you were to see a change in vector composition because of the changing land cover. I don't know how well you can see that. That's just the 2 areas that we're studying, Nongran and Barato. And essentially it's just to show that there's this kind of mosaic of different levels of forest and cleared areas. And in the cleared areas it's usually rice fields. And this is the sort of kind of typical village that you would find in Southeast Asia. So very different setting to malaria transmission areas in Africa. So much greener, much wetter. This is one of the wettest places in the world. So you often see these kind of hills with small valley bottoms with rice in them. So this is the Nonglang area. Another place in the Nonglang area, this is even more forested, so you actually could see forests going off quite far into the distance with these forest streams where minimus would be breeding, for example. So we might expect to see, to match the mosaic and landscape, we might expect to see a bit of a mosaic actually in the mosquito species that are present too. So the forest species, minimus and bimai, as well as these rice breeding species, especially Culispaces. Oh, and this is the other area. So even though these areas have similarities, there are also differences within them. So we can't assume that the malaria transmission is going to be the same in the two areas. So this is Barato, which is the area further to the west. And it's hard to tell from this picture, but it tends to be much flatter, more open, less hills in the background. There are other differences too. So you can see here it kind of it's flatter, more open. They also seem to keep a lot more livestock and animals quite close to the house as well, which I didn't really observe that in the other area, Nonglan. So why do we care about, you might think that it's the same disease, does it matter what's transmitting it? But there could be many reasons why changes in vectors could actually change malaria epidemiology. So for one thing, because they use different habitats, they peak in abundance at different times of the year. So again, they might also be affected differently by climatic change. So minimus and bimai are very much dependent on the rainfall. So for stream breeding and bimai with it uses pools in the forest. And so they tend to peak in transmission in the main rainy season, which is sort of June, July, August. Whereas Culispaces, because it breeds in the rice fields, it tends to peak a bit later in the year. So the rice gets planted in about March, April, and it's irrigated throughout the year, and it's harvested in about November. So these numbers tend to peak in November when they've had the maximum amount of time to build up in number. So abundance peaks could be at different times of year. The reason that might matter is either it could affect the time of year when we have maximum transmission, or even worse, it might actually extend transmission. So it might be by having more vectors, it could make the malaria situation worse because you might have, there might be a synergy between the two, where you get transmission by some species later in the year and some species earlier in the year. Also, as it happens, the original forest breeding species are not susceptible to insecticides, whereas the rice breeding species actually are, because they've been exposed to so much insecticide for a long period of time because people use, they're doing pest control in the rice fields. So as a knock-on consequence of that, a lot of the rice field species are resistant to the pesticides, and it's the same pesticides that are used in the bed nets and for house spraying. So that might mean that the malaria control measures would no longer work. And then there's a whole other lot of things that might affect how good they are at being malaria vectors. What time of day do they bite? People are now using bed nets. So if some vectors species feed later at night, the bed nets will be effective at protecting people. But if some species bite earlier, the bed nets will be less effective. And we know from previous studies that the time of biting of mosquitoes can be species dependent. They might choose to feed outdoors versus indoors, or they might choose to feed on people, be anthropophilic versus zoophilic. So these could be differences in species biology that would therefore affect the malaria transmission. This is going to do things like affect the number of infective bites, yes, which again is part of that Arnold equation for transmission. So the research aims here, which we haven't really got very far with yet, we're just starting to collect data, but I think that this is quite a common approach now that people are often taking. So they've got this overall question is, how is land use change affecting disease transmission? So our specific idea here is to look at what the effect is of this increase in rice growing on malaria. And we're going to do a couple of different things. We're going to build some spatial models, which would aim to predict the spatial distribution of mosquito species that we find to be vectors, larval breeding and malaria. Potentially one could actually put climatic variables in there too and predict future climate change. That's not what we're thinking about at the moment. And so there is so we'll use land cover information from remotely sensed data. So this is working with other people in the university that use geographical information systems. So they'll gather the satellite data. It's an incredible spatial resolution, so like 10 to 60 meters, so really fine scale resolution, collected actually almost on a weekly basis. So you can really look at changes in land cover with a fine temporal and spatial resolution. And then we'll combine that with information that we're collecting on malaria distribution and the mosquitoes themselves, where they are in the landscape. And we'll also do some genomics as well. We want to look at this cubus species. We want to know if it's a species that's been there for a long time but in low numbers and it's just increased in abundance. So is it an ecological response? Or it might be that it's actually an invasive species and that it's invaded into this area and is spreading because the environment is so suitable for it. So those kinds of demographic changes actually leave different signatures on the genome, so we can use genomics and the sequence data to try to distinguish what has been happening historically. If it turns out to be an invasive species, that will be very concerning because there's no reason. So remember, this species comes from mainland India. If it gets into Meghalaya and if it can survive while there, other than a hill range, it is a big hill range going over into Myanmar, but there is the potential it could spread much further and be quite, quite devastating in terms of malaria capacity. So we're going out collecting mosquitoes, which is hot, sweaty work. This is somebody collecting mosquitoes in the rice fields. Then we get to grow them up so we can see what they are, and they're a bit bigger. And actually we collect adult mosquitoes using these light traps. So this is a light trap outside somebody's house. So when it gets dark, the light will turn on, the host-seeking mosquitoes will go to the house, which is how people are normally infected in their own homes by the mosquitoes entering the house and feeding on them. So everything we collect is GPS tagged, so we always have a geographical coordinates for it. So that means it can go into this geographical information system and we can compare what species we get to the land cover on that area from the remotely sensed data and build models and hopefully do some predictions. This is really preliminary data, and I'm only showing it just to mention that so far at least these are the different villages we've been collecting at. And we are collecting the forest species, minimus, and this is bimai here. It's one forest species. I think this might be the minimus, another forest, oh no, that's the minimus, another forest species. And then this is the cubus species. So this Nonglang has got huge rice fields. So it could be that this is all coming from the rice fields. We're getting it at a few different sites. So that's what we're working on. So we're interested in the effect of land cover, but that's just one component of malaria risk. All of these things are going to affect it. So things like how close you live to the larval habitat. People have also found that proximity to domestic animals makes a difference. And they've argued it both ways. They've said if you live next to domestic animals, it's bad because it attracts the mosquitoes. They've also argued that if you live next to domestic animals, it's good because it attracts the mosquitoes, but it also attracts the mosquitoes that would otherwise have fed on you. So it actually reduces human biting. And also don't forget, for malaria transmission, you have to have successive feeding on humans, don't you? You have to have one feed on a human, followed by a second feed 10 days later on a human. So potentially animals can dilute that effect. I pointed out to you that area in southern Myanmar, which seems to be a very high-risk area for malaria at the moment. Part of the reason for that might be rubber tapping. So that's an area where there's lots of rubber plantations being planted, and people go out at night to do the rubber tapping. Okay, I don't quite know why, but I think when you get the resin from the trees, I think it comes out better in the evening. People hunt. Might not be surprising to you to know that people also drink. When they drink, they tend to end up sitting outside late at night without any protection, or they might go to sleep and not use their mosquito nets. House construction might be a massive factor. There's the different kinds of houses that people live in this part in Meghalaya. And you can imagine that with these, it's pretty easy for mosquitoes to get in. There's lots of open access areas, there's gaps in these bits of the wood. Sometimes there's huge open spaces at the top that the mosquitoes can fly in. And you know, if you're a poorer person, you might have a house like this, and a richer person might be better protected because they've been able to afford a house, or they can perhaps try and close it up a bit more at the top. Another issue might be adaptation to man-made habitats. Again, talking about that area in southern Myanmar that had high malaria, which is basically down here somewhere. This is southern Myanmar, just here on the border with Thailand. And we have done some work in that area too, and what many people have noticed is that there has been a change in the mosquitoes there. So this is the major forest vector, and now it's able to breed. So this is the kind of original habitat you would find it in. So this is a pool in the forest, or you might find it in elephant footprints, which are not so easy to find these days. But instead now it's breeding in these village wells. So only in this area, not everywhere. So it's managing to get into here and lay its eggs, and you can get them in really large numbers sometimes from these wells. And of course every village needs at least one well, and actually will have many wells. So again, you know, one of the problems we have to think about is the mosquito's ability to adapt. And based on the presentation from, sorry I don't know your name, that you gave on ticks and flies, we saw that mosquitoes might not be great within their lifespan, and not as good at ticks anyway, as coping with variations in environment. But what they have on their side is huge reproductive capacity and huge population sizes, so that means that they can potentially adapt in the sense of evolve. And we think that they're evolving to these new habitats. And that decreases their reliance on the forest. So now they can use the rubber plantations to get shelter in the daytime, if they need it, and then use the village wells. So it might be that these are the changes that are driving high malaria in this area. There can be invasive species, insecticide resistance, change in feeding times, and you could probably just go on and on, adding lots of different things. And I guess my point is this, really, and this was a quote which I think I've seen before, but not for a long time, and it's in the Writer paper. So Hackett was a malariologist, a British man who worked on malaria in Europe, I think also in Africa, many, many years ago. And this is a great quote from him, I think. So he says, everything about malaria is so moulded and altered by local conditions that it becomes 1,000 different diseases and epidemiological puzzles. Like chess, it is played with a few pieces, but is capable of an infinite variety of situations. And so I hope I've showed you, just with that very specific scenario of malaria in Meghalaya, it's just how many different factors come to bear when it comes to malaria transmission, and climate is just one of them. I'm not saying it isn't important, it clearly is important, but you can't look at climate in isolation and make predictions. So just the last couple of things. So we also need to look at the context as well for this. This is in the recent malaria report that's come out by WHO, the World Malaria Report, and looking at changing malaria incidence. And some countries now have got incredibly low levels of malaria. So places like Bhutan have just got a handful of cases a year. Thailand has relatively low numbers, just really left in its border regions. Other countries like Myanmar have a massive burden. Actually, you can see that better here, can't you? So you can see, comparing from 2010 to 2017, the drop in cases in Myanmar. So this is a consequence of the political change that's taken place, donors coming in with bed nets and giving them to the Myanmar government, who've then been able to distribute them widely. And so probably this is mainly bed net distribution, better drugs, better public health care. So a massive drop. Even Thailand, which didn't have much malaria to begin with, has gone down, probably partly because the malaria on its borders with Myanmar is decreasing. Bhutan has it's almost a situation where it's going towards malaria elimination. And actually, what's really quite unusual as well is that really as a consequence of a lot of different efforts, but especially the bed nets, we're actually seeing countries being really successful in getting towards, being on target to reach this milestone of reduction to 40% of what it previously was by 2020. And so lots of countries have already met that target and are definitely on the way to get there if they haven't already got there. So as I mentioned, this is a result of LLINs. I talked to you about this in the previous lecture. This is long-lasting insecticidal nets, IRS, indoor residual spraying, more effective public health. Also the test and treat policy. As malaria becomes lower and lower prevalence, what WHO advocates, but it's quite expensive, so it can't always be carried out. This is test and treat policy. So the idea with this is that it's important that every suspected malaria case is tested and treated so that you're not wasting drugs and potentially causing drug resistance by giving people drugs unnecessarily, and making sure that every infected person is treated. I already said before that that can be done, most commonly done with RDTs or microscopy. This needs a good trained technician, or potentially PCR, but that's not routine. But one of the issues with that, it is effective, is whether or not you should have active versus passive case detection. So active case detection, you actually go out to villages and mass screen and treat. So there are studies ongoing as to how effective that is. It's very costly, but it might be that as countries develop, get more money, or more money is provided by external donors, that there might be a move towards that. So that's the kind of context in which we have malaria at the moment. I'm not saying it's the same necessarily for all diseases, and then there's always these surprises that come on us, like I don't think anybody expected Zika to be quite the problem that it was. But certainly with something like malaria, it's difficult to know what the situation would be in, say, 2030, 2050. So we're building these climatic models about what will this malaria be like in so many years' time. It's really hard to say, isn't it? Because what this is telling us is that that situation is changing on a year-by basis really rapidly at the moment, with quite effective controls. And one of the things we're hoping we might be able to work on if we get the money is really environmental control. So with the rice growing, for example, it looks as if the changes in rice and how it's grown, so increased irrigation, people are moving to try to get 2 crops per year. That's potentially really bad news for malaria transmission if we have these rice breeding mosquitoes, but it might be that actually there will be relatively easy solutions. That's easy scientifically, not necessarily easy to implement in policy. But it might be that you could do things like just periodic draining of the rice field, or actually that you don't even need much water to grow the rice. There's a big movement that's saying that you should have no-till agriculture, minimal amount of water used in rice growing, because you're taking water out of the whole ecosystem when you divert it into irrigation. So it could be that there will be environmental control measures that you could take to reduce malaria in Southeast Asia, actually also in parts of Africa where they grow rice as well. So we've spent ages, or I spent ages, sorry, talking about that. How about we take just a brief break for 2 or 3 minutes, a quick look at these questions and leave it there. Does that sound okay? Do you have any questions on the malaria in Southeast Asia?
I've got a question in general.
Yeah.
Is there, so mosquitoes that aren't vectors in certain areas, is there a possibility that they then can become vectors if conditions change?
Exactly, yes, very much so. So things like some of those species like Anopheles nagipes and Anopheles philippinensis are usually not considered to be vectors, but when the numbers increase, because they can breed really well in rice fields, they can reach a threshold where they can start to transmit malaria. And again, it comes down to that Arnold's equation. If you look at that, the number of bites that they can deliver. So they'll often feed on other species as well, but if they're numerous enough, there'll be enough infected bites that they can transmit. And so we've seen that, certainly I think in Laos, there's been a lot of intensive rice growing, and the malaria situation has really increased, and they've turned out to be a vector. So yeah. So the vector status can change depending on the environment. Obviously nothing to do with climate.
Yeah, that'd be interesting in the future, because they're trying to grow drought-resistant rice, aren't they, for climate change?
Is this from Amanda?
Yeah.
Okay, I don't know much about this. Okay, right,
so
that's interesting. Well, that could be a help.
Yeah, so it might be that it's all linked together. If you can grow rice that takes less water, you're eliminating, I guess, the need for big areas.
That's right. And actually irrigation has really deleterious effects as well, in the sense that it's taking water out of the ecosystem. So Suzanne Schultz, I don't know if you know her, but she's working in Tanzania, and they're taking out masses of water for the rice growing, and it's kind of taking out water that would otherwise go into like the Masai Mara and other places. So it has massive impacts over a huge area, these rice growing schemes.
Yeah, because there's a conflict at the moment. I don't know if it's that one, but definitely in Africa. I know it's to do with the Nile, I think, because they've siphoned off so much of the Nile for irrigation. There's parts further down the south of Africa that are losing so much water now.
Yeah, and presumably in different countries. So, but it's really a problem, isn't it? Yeah. I don't think that would be going the other direction, I mean, I think that's a problem in lots of places. So, yes, it's not just about vector-borne disease by any means. It gets quite.
It's all linked together.
It's all interrelated. Yeah. So I have some other papers, which I don't know if you guys want to. We're not going to go through them now. There isn't the time, but I'm happy for some people to take them if you want to, or else I could make them available maybe on the website. Would that be useful? Because I was thinking there would have been time for people to bring talks to work on these in the session. I tell you what, I'll get some. See what I've got here, and you can choose them. So. I've got a couple here on ecological assessment of Zika virus. I've got some on, I've got a couple of copies of each. Got something on Mount Kilimanjaro, and that's quite interesting because it's about 10, I think this actually has got some data to look at how malaria has shifted in response to climate change. So I've got that one, I think I've got something about Tanzania maybe, yeah, malaria and dams in sub-Saharan Africa. I'll tell you what, I live here at the end, you can come and see if you want any of them.
I didn't know. I just thought it was that corner. The one there, yeah.
So should we just have a quick look at these questions and then we'll leave it at that. So, I mean, I just kind of pulled these questions out of the air. We don't have to be restricted to these. We can just talk generally. So, I mean, what do you think of the climatic models? What do you think? What are they taking into account? What are they missing? How useful are they?
I guess the problem with climate change is that there's also going to be a lot of extreme events that we can't predict. There's going to be like flash floods and sort of changes like that no one's going to be able to predict how it's going to affect.
I guess you might predict it's more likely to happen, but you wouldn't. It would be quite hard to have any certainty to it. Yes. Yeah.
What about changing wind pattern as well in the climate predictions? Because surely wind massively affects it.
I don't know. I mean, it definitely affects it on a very small spatial scale. If on a windy evening you'll get no mosquitoes. But so I guess if there was a general increase in windiness in certain areas, it could have an effect. And I'm sure you're right that you can't model that.
Yeah, I'm not really sure.
I don't know either, but I think that would be quite difficult. So I don't think it probably isn't taking that into account, and it could have an effect. I think a lot of the biology of the mosquitoes is not taken into account. I'm not convinced at all by that Southeast Asian paper that I showed you the data from. That was, I mean, it was just as far as I could see, it was basically just saying, oh, everything will just shift north a bit because it will get hotter. It will get too hot for them down in the south, and in India where it's already quite hot for other climatic reasons. And it'll just shift up north a bit because there'll no longer be the cold stress. It seemed like there wasn't anything more to it than that. I could be wrong, but I wasn't convinced that it was very. Yeah, so.
I guess it's showing that there's at least going to be like a range northward of like climates that are suitable.
I think that's a really good response. Yes, you're absolutely right. It's not going to help you perhaps work out where in Meghalaya it's going to get malaria. But what it does tell you is that perhaps in China, where they may never have had to worry about malaria before, now they should worry about it because in the future it could be there if they've got the vectors. So I think you're right, yes. So I think it is, I think you have to just think about what information is useful from these models. So I think it's useful in that context, I agree. What about any of the other contexts that you've seen? Did any of you read the paper on malaria in, I think, in the Ethiopian highlands and in Colombia? I think that was one of the papers that I put out for the case study that you can do. So in both cases where you've got these highland areas, I think you can, as you can imagine, that as it warms, there is the potential for malaria to go into higher altitudes. So I think where you've got that, basically showing that there is a shift in the potential for malaria to be present, it is probably helpful. I don't think it's going to give, whether or not there'll be malaria there will depend on the control and a whole load of other factors as well, I think. And I think that particular Southeast Asian paper lacked a lot of realism in the sense that it tried to treat malaria as one disease, when pretty much everything we know about malaria is that it's lots and lots of different. I mean, it's just everywhere you go, it's a different set of factors that combine to result in malaria transmission or not. And I think that's why it's been so difficult to eradicate. And this, how might the ecology and behaviour of the vector and humans determine the burden of disease? That was kind of covered in the writer paper, basically. He went into that at quite a lot of length. I mean, I think he has quite I quite like this paper, but I think it has quite a bee in his bonnet about climate change modelling, and that he did, I got the impression that he thought it has limited use because there's so many other things that are important. So any comments on ecology and behaviour?
I guess that as if climate change got really bad and sort of sea level rising and areas change, I guess there's going to be a move of urban areas and a move of maybe people having to live in different places, which could all have a knock-on effect. Like you said, if places that are more rural, then are going to have to be inhabited and wells sort of dug. That's going to affect the distribution and also the amount of people that get in. Okay, so you're talking about kind of, I think you're getting at actually one of the points that I think the other guy raised, and Ogden, which is that, and I thought his paper was quite interesting because it's a bit more balanced, but he was arguing that it's not the direct effects of climate change, but the indirect effects that might actually have a really big significant effect on the disease burden. So it's like how people respond to it. Will they be moving? Will they be shifting where they live and how they live? And actually, what amount of conflict will it cause? So one thing we know is that when you have conflict, malaria, skyrockets. So probably the reason there's quite a lot of area in Rakhine is because of the conflict, the difficulty to work in that area. In the past, on the other side of Myanmar, the Shan Plateau going over towards Thailand has been a massive no-go area for a long period of time because of conflict with the Burmese government. And that's always had huge malaria as well. So as soon as you have conflict, I think in Rwanda as well, when they had all the problems a long time ago, there was a huge increase in malaria. So I'm guessing there'll be a lot of conflict as people lose access to quality land and population growth as well as climate change.
Are mosquitoes affected by electronic light? So if you had there's loads of incentives in there to introduce solar into lots of African rural areas. If they feed at night, when you have a light, will that shift?
I think that's a really good question, and I don't know the answer. We definitely, I know if you sleep and you've got no lights, you get bitten by mosquitoes. If you sleep and you've got lights, you get bitten by mosquitoes.
Okay.
So they seem to find you regardless. But the way that we catch the mosquitoes is to use lights. So they are definitely attracted to the light. And I guess that's something humans have always done, isn't it? If we didn't have electric lights, we'd have had fires or something. So mosquitoes have presumably learned to be drawn to the light as well as the smell. So but how much of a difference it makes, I don't know. But yeah, it could be. And I realise that is not on our forms in any way. We don't look at that when we collect the malaria data, even though some of those villages don't have electricity. And so the lights go off really early. If there is electricity, the generator turns off at some really early time. So it could have an effect. So I think that obviously human behaviour makes a big difference. If you live in a house and you go in at night and you put a screen up, you can protect yourself from mosquitoes. And one of the things I really tried to convey is that the diversity of mosquitoes and their varying ecology makes a massive difference. What about the spatial and temporal scales at which these models might be useful? What do you think about that? I think you kind of answered that question earlier, actually, when we were talking about. So what about the spatial scale? I think they tend to be very general, don't they? Because if I'm saying to you, well, we need to be able to predict different areas on that side of the village versus this side of the village. That's super, super fine scale, but that's obviously not what these models are going to predict. They're going to say southern China is at risk, or this altitude in Ethiopia is now at risk and it wasn't before. So they're going to be really broad brush, I think. unless they can incorporate more biological reality. So I think that's a big, yeah. And what about the sorry, go on.
Which is interesting because, like you said, like when it was in the UK, even though it was in the UK, it was kept to these more marshy areas.
Yeah.
So saying, oh, China's going to be at risk is good, but there's going to be areas in China that are more at risk than others.
Definitely. So the climatic variables on their own will not be sufficient. They'll be able to say that zone has got the right climatic variables, but then you will also have to take into account things like might be rice growing or something like that. You know, so the land cover and actually population density too, including population density. So they are useful, I think, in a really broad sense, but they're not going to give you fine-grained information. And what about the temporal scale? I guess I was kind of trying to talk about this at the end of my thing, which is, I mean, I guess most climate scenarios are what, 2030 to 2050, I think the most sort of common. Well, for malaria, I don't know what the situation would be in 2030.
Time as well, because like a lot of the flies have such a short life cycle. I guess predicting them on like such a long time scale, like 30, 40.
They can adapt and evolve. You know, I mean, I think things like Aedes aegypti, when they've gone into the United States, and also Aedes albopictus when it's gone into Europe, it looks as if it's shifting slightly north in both places, and that might be just due to a little bit of adaptation to cold weather, which could either be behavioural, getting out of the way, or might not be able to tolerate colder things.
Could that continue to happen then? Like?
Yeah, easily. And other mosquitoes, so things like there's a Culex species in London that's adapted to living in the underground. You know, so all sorts of. Unfortunately, pest species are really good at adapting and evolving, like that one that's switched to breeding in Wales, and so those are the things that could be complete. I mean, they could just change everything. And of course, the parasites can change too, so that, you know, what they can be transmitted by, how much disease they cause coming out of wildlife. So I guess with the temporal scale, with malaria, actually with all of these diseases, I think it's hard to know what the control situation will be in 10 or 20 years' time. I mean, people have been, I think maybe malaria in Southeast Asia might be sorted. Maybe. Malaria in Africa, I'd be amazed if it was sorted, because it's such a massive problem and it's such a much bigger burden in Africa. And there's so many more difficulties in terms of just the size of the country, of the continent, of the, you know, a lot more poverty, a lot more, I mean, much greater levels of transmission that are currently happening. So I can imagine that in many places in Africa where malaria is endemic, that we won't have got rid of it by the time these scenarios kick in. But I think, I don't know, my guess is that they're just tweaking things a little bit, just saying, oh, go a bit higher up the mountain. And I think most of it's going to still, the potential for malaria in most of Africa has still been, in the parts of Africa where we already have malaria, will still largely be there.
Because it's quite also largely socio-economic kind of problems.
Very much so.
Temporal scales don't include any of that. But you could, I don't know, one country could have massive political reform.
I mean, that's why you see this massive difference between Thailand and, for example, Myanmar. Thailand got rid of malaria pretty much decades ago, except around the edges where it couldn't control people coming over the borders and bringing in new malaria. But they had amazingly effective treatment, so all treatment was free. So if you went into a clinic, which you could easily access because of good road infrastructure, and because you had been educated that you knew you had to go to the clinic if you have a fever, you get treated, they do a follow-up, they go back, they spray all the houses in that village.
Thailand's so interesting to me, having travelled around a bit of Southeast Asia, Thailand's so interesting to me because sort of you go to like Vietnam and Myanmar and it feels so much more rural, and then you step into Thailand and it's like being back in the Western world again.
It very much is, but there is still lots of rural areas in Thailand as well, of course. But it, and I've worked there for a long time now, and I've really, it's changed so much. But you're right, it's a very, very developed country now. Yeah, it's not. But so, and I think Myanmar will change rapidly. But it is, most of these diseases are diseases of poverty, and if you know, I think the situation in Africa is biologically much more difficult. There's a lot more. The environment, the vectors, you can get really, really high levels of transmission there that make it higher. But I bet if we had that in Europe, we'd have got rid of it. Although the argument is usually the other way around. The argument is that one of the things that has made development so difficult in Africa is because of things like the burden of diseases such as malaria, which have such an enormous toll on people, you know. So, but yes, if all of a sudden we had that malaria burden in Europe, we would have the wealth, I think, to throw at it and to solve the problem.
People go to like doctors just for a minor thing. So as soon as they got a fever, that'd be the first thing they do. So they know.
Yes, yeah. So it's just such a different situation. So yeah, so it's hard to predict. But I think maybe in somewhere like Southeast Asia, in some of these countries, hopefully that, you know, I'm not sure that the time scale for which we're doing the malaria control on, I'm not sure how relevant the time scale of the climate change predictions is going to be. Okay, I've got these papers if anybody would like them, you're welcome to take them. Have a look, different things. They're not all, there's a couple of copies there. So I'm just thinking about how to do this better next year, because this is the first year I've done this. So asking people to come up with a paper and give a talk didn't work, did it?
I thought the discussion was way better.
Yeah.
Oh, okay.
It was good.
Okay.
I think that's like one of the most productive seminars I've been to.
Oh, good. Okay, well that's something. That's good. I'm just trying to think how to get more people to participate then.
I think because it was the last week as well.
I think you've got a hard slot last week on a Thursday.
And this is the last lecture
Oh, is
that
it?
we have before we
okay.
break up. So I think a lot of people might have gone home.
Yeah. Okay. So do you, okay. Well, maybe that's always going to be a problem, isn't it? If I'm in the same spot next year as well.
I think this topic is a bit nicer to have more like a discussion as well, because it's not just kind of like the LWCCR, it's so science based, but
Is
it's
it?
because it's like quite a mix.
It's very complex, I think, and then actually the reality is with a lot of these diseases, it's down to politics and economics, and you know, not. I think a lot of the sciences, well, not a lot, but some of the sciences are. Well, thank you very much for those of you that came and for the discussion. Oh, good. I'm glad you found it.
Talk to you.
Yeah. I think
Do you agree?
Yeah.
With regards to like the exam, would the essay be centric on climate change then, or?
I mean, that's what the topic is, isn't it? But having said that, you have to think about climate change as part of the wider context, don't you? So, you know, I think it is relevant, even within this module, to ask the question, to what extent is climate change going to be responsible for vector-borne disease versus other changes? So I think everything. I think all the other aspects as well you should think about too. Because I think the reality is not simple. Yeah. So yeah. So I think compare and contrast probably.
I went to
Don't kill me, makes you very happy.
with Team Uganda.
I can't understand why.
Okay, right. Where did you go?
I kind of got myself a part. No, it said take your own risk. I was like, oh my god.
So they're literally like giving out like
We have a box that we can take them from anyway, so it's like testers. So I think a lot of testers.
Got malaria.
It's fine.
She's
just
like, oh, it's fine. I'll just get the medicine. Like they're so. I guess to them, it's so common. Yeah. Yeah, maybe, yeah, because we were all like, oh my god, are you okay? And she was like, yeah, I'm fine. She just didn't understand.
It might just slightly on rotary oil or something, or one person might break off the mask and skin. I don't know. Use at your own risk, but it should be fine.
Because of the because it's natural, like if one person has a reaction to it, she would like change the recipe. But like women to be 100% natural.
To go to the lake and do everything like that. And
I've accidentally put honey in when I'm not meant to put honey in, something like that. I don't know if there's honey in it, but it's free.
Yeah, because we've got we got told her own name.
Like it's not like
I was really careful not to.
She just did it late.
It's just like a mask. But it was, but everybody stopped it. It's hard.
It's so sick.
And you don't realise how lucky you are.
Why like having the test that you wait for the shop floor once it's half finished? I want like things that are like equivalent price, that's £7 in
Definitely, I'm sure.
Thank you.
Thank you very much.
See you guys
On the economic development, you know.
Yeah, definitely.
If you're ill with all these different things, and you also change your attitude to long-term planning versus short-term planning, so it has really big impacts. So, did you like Uganda?
Yeah, I loved it. Yeah,
It's a lovely country, isn't it?
Yeah,
it's really, really lovely. Did you guys manage to go and see some nice bits? I mean, you know, touristy bits, I guess. I mean,
not too much, bits and pieces, but it's a really interesting country to work in, and I found the people are just so lovely.
They're lovely, aren't they?
Really interested in talking to you, and often get followed around going Muzungu, Muzungu.
Yeah.
But yeah, really.
I mean, it's a long time ago now. I partly grew up there when I was really, really little. But yeah, but it's changed. I mean, like all these places, of course, it's changed a lot. But it is lovely. And I had the opportunity to go back more recently for work, but not on malaria. We were working on the Ades in the forests. And yeah, that was great. It was wonderful. I really enjoyed it.
Yeah, I'd love to go back one day.
Yeah, me too.
Do some more volunteer.
Although I'm not going to go wading in and walking.
Learn your lesson.
Thank you very much.
Thank you very much. See you.